Hello, everyone. I've got 12 o'clock local time here on a rainy day in Smyrna, Tennessee. I appreciate y'all joining us today for our April 2021 webinar. Just a reminder for everyone that we're going to hold all the questions to the end. So if you have a question that you think about during the presentation, just pop that into the chat box there, and we'll address that at the very end. There are a couple reminders that I wanted to hit on before I turn it over to our speaker. Let me switch slides here. So the first one is that we are still soliciting articles for our next transmissions newsletter. If you have anything that you'd like to share, please contact editor at hydrologicwarning.org. The deadline for submission of articles is May the 1st. Our next webinar in May is going to be on other data collection. Ryan Guerrero from IntelliSense has been so kind to speak in that one. So if you go to gotowebinar.com, click join, you can enter that number, 915-939-859. I'll switch back there. Sorry, this was on loop. And that'll register you for that webinar so that you get all the reminders and don't forget about it. And then I'd like to remind everyone to follow the NHWC on social media. The best place to find us is probably Twitter. At NHWC News is our Twitter handle. So we post on there routinely, especially when we have new events coming up or coming out with some new information. So I will stop sharing my screen. I'm going to turn the presentation over to our speaker today. If I can find his name. While I'm doing that, I'll introduce our speaker. So our speaker today is Brian Iserman. He's a hydrologist with J.E. Fuller Hydrology and Geomorphology, based in Arizona, from what I understand. Brian's been a long-time member of the NHWC, and in fact, he's actually the editor of our newsletter. So when you're sending your articles to editor at hydrologicwarning.org, that's who our articles are going to. And so we really appreciate Brian both speaking today and also for his longtime contribution to NHWC. And with that, I'll let you take it away, Brian.
Awesome. Thank you, Brad. How is the sound and the visual? Do I have it all going right?
So I'm hearing you just fine, and I can see your first slide, your introductory slide right now.
Great,
If
thanks.
anyone has any problems seeing things or hearing things, just feel free to pop it in the chat box and we'll try to address it as quickly as possible.
Great, and thank you, Brad, and really thanks to the Training Professional Development Subcommittee. It's a lot of work and effort to put these together. I know you guys have done a lot of coordinating, and Brad, I don't even know all the technology you've had to figure out to get this going. Must have taken some time, so really appreciate that. Yeah, let me give just a little more background that'll serve as context for the rest of my talk. We are here in Arizona. I was born and raised here, and I've spent my entire career doing, arid lands hydrology. So with an emphasis on flood warning systems, dam safety, all that. I installed my first alert gauge in 1987, working for Pima County Flood Control District in the southern part of the state. And so that'll give you a feel for, the type of environment I'm used to working in is like what you see in the first page here. It's an arid environment. Floods come not too frequent, but when they come, they're quite large. And other times we have dry channel beds. So that'll tell you, how I look at things a little bit. And so if you're on the East Coast or in the Midwest and think, well, that's not how we do it here, it may not be how you do it there because you have rivers with actual water in them and that kind of thing. So I don't know how you people do it with rivers with water in them. I like to work in dry rivers. They're much easier to work on. So anyway, so we do a lot of modeling. I'm going to figure out how to make this thing advance. There we go. Okay, so here's the syllabus. It's very simple. Kind of two main things that I want to emphasize today. in about 50 minutes. We'll have about 10 minutes or so for questions. Sensor types for collecting stage data, and placement. Really, that's it. It's going to be pretty simple. And we're going to just dive right in now to sensor types. We'll look at a few of the most common ones, including shaft encoders, pressure transducers, radar, ultrasonic bubblers, and acoustic Doppler profilers. I've got experience with some of these, but not all of them. So I'll admit where I have little experience, and I'll share the experiences I have with the more common types of sensors that are in use out there. Shaft encoders are simple. We'll start there. These are the oldest type that we've used. In the old days, they weren't digital. They had chart recorders with pen and ink and a paper chart. Nowadays, they're digital. They're even SDI-12 type sensors. They're very simple in concept. There's a shaft that's turned by a pulley here. When the float goes up, because the water level goes up, the weight pulls the chain down the other side. It turns the shaft. The shaft is connected basically to a magnet arm with a bunch of Zener diodes, sometimes the older ones. I don't know how the newer solid state ones are, maybe the same. And it lets you know that the position of the shaft has changed. So very simple digital type sensor. Here's just an example in the lower right of what a modern one looks like. This is an Ott brand, and it's quite small. It's about a 3-inch square chassis for the shaft. Basically, there's a chain. It's plastic. It's not an actual cable with steel beads on it like in the old days. And there's just a plastic float. And in the old days, we used like a hollow metal, sort of a float, and they'd get holes in them, and then they'd sink, and there's all sorts of troubles. So some advantages and disadvantages of shaft encoders. They're still handy. We use a few of them, not many, in all the sites that we take care of for our clients. They're considered a contact sensor. So something is in contact with the water to measure the water. So that's the general category type of sensor. They're relatively inexpensive and sturdy. There's not a lot to go wrong on these. I think we've only broken one over many years, and it just quit. They're digital, obviously, and they do have SDI-12 options available now too. They're good in ice. This lower left photo here shows a seepage outflow monitoring station at the bottom of a high hazard dam here in Arizona. It's up about 8,000 feet, so it does get very cold there in the winter, and the water that's seeping out from the principal outlet here of the dam freezes, and it gets into a solid block in this behind the weir here, behind the weir plate. So, a pressure transducer wouldn't have been a good option in there. We decided to just use a real simple technology like this. If the float gets stuck in the ice, it doesn't matter. It's just going to stay there until it thaws out in the spring. So they do require a special housing, a little stilling well like this. You guys, you've all seen this before. You've seen stilling wells out there. So there's sort of the whys and the whats of that type. Now, further on, I'll show lots of photos of just examples of one, but shaft encoder I won't really cover any more than this. So this is an example of a small site that uses a shaft encoder that still works really nice and reliably. Pressure transducers are probably the most common sensors out there for flood warning types like us. There's two types of pressure transducers, the vented and the non-vented types. I remember using my first pressure transducer, maybe it was like 1990 or something, when they first came out. We thought they were amazing. It was housed in a 4-inch, piece of PVC pipe about 1 foot long, and is real bulky, and the signal conditioning was inside of it. So if you wanted to calibrate the span and zero pots, you had to take it apart. But we thought they were great, and they last like almost a year. Nowadays, pressure transducers are quite sturdy. They last a long time. They're a good, relatively inexpensive option. And basically they do just what the name implies. They measure the pressure of the weight of the water on top of them. And some pressure transducers, like this particular one model that's pictured here, it's an SDI-12 I believe it has a 0.005 foot resolution, and we're using it at a site where we need real fine resolution at a fish hatchery. For flood warning, we wouldn't care so much about that kind of resolution, but for this one we did. So, you know, we're slowly, as the old analog sensors die out, we're replacing them all with SDI-12 because of reliability, their stability over time. They don't drift on calibration like analogs do. If you've used a lot of analogs, you know you have to check them pretty regularly, you know, at least every 6 months to a year to see if they're on calibration still. With these particular types of sensors in general, you know, they're going to have an issue with sediment. They do well in sediment. We have a lot of high sediment yield environments where our bed loads are pretty high, and they do just fine as long as the sediment doesn't compact around the sensor and thereby bridge any pressure that would go to it, bridge it around the sensor. So as long as it can sense the pressure, it's fine. So they do have a little thin, often a titanium membrane, usually down there near the head there. And it's pretty sensitive, and they can become deformed over time, and so they drift a little bit. These SDI-12s just don't drift much. There's some we've just, for years, we haven't had to tweak them at all. Sturdy-ish, I say. I mean, they're getting better and sturdier, and you just, once they're housed well in a conduit, I'll show you some examples, they'll last a long time out in very harsh environments. We've had them survive, you know, huge debris flows if they're housed well. So we'll come back to PTs later. There are non-vented PTs. So the previous one was a vented PT. That's what we use because you can do telemetry. We have a client that likes to use these unvented PTs because they're just doing data collection. They don't care about flood warning. But I thought I'd include them anyway because you'll see them out there. The big advantage is they're super simple to install. You don't have conduit running from a channel bottom up to your telemetry station up the hill or over on the side of a bridge or whatever. They just need a little short section of pipe bolted with a couple bolts into a rock or somehow, you know, hooked to a post or whatever. They're a little more expensive than a vented pressure transducer. They have internal logging, internal power. So obviously, you know, you've got to do your maintenance on it, change the batteries out. You have to manually download the log, all that. Not helpful for flood warning, but good if you're just trying to inexpensively collect some data. So won't spend much time on those. I don't care for them. You have to do post-processing too. You have a barometer nearby hung in a tree somewhere. After you take the log data off, you have to post-process to separate the atmospheric pressure changes from the water pressure changes. A vented pressure transducer is vented to the atmosphere, so it passively discounts any atmospheric pressure changes. So you're only measuring the depth, the weight of the water on top of it, and not the weight of the atmosphere on top of the water. So hopefully that makes some sense. Radar, these are becoming more and more popular. We're using a lot more radar now. We really like the radars. They're really handy if you have an overhead place you can mount the sensor. The basic concept is they use the radar range of the radio spectrum, the real high frequency electromagnetic radiation, to actually measure from the unit down to the water, and it gets a return back, and it measures the time it takes to travel down to the water and back. Because they're super high frequency, they're not thrown off much by temperature changes of the air and all that kind of thing. So that's the basic behind them. Here's in this picture just a few different ones. These are a couple Endress Hauser brands. This is I believe this is an FTS brand, but it's sold through Campbell, I think. FTS makes a really nice one. It's kind of our favorite now. Their SDI-12 unit is moderately priced. It's low power. It just works really nice. It's easy to mount and everything. So radars are non-contact sensors. They're, you know, about your best option out there for keeping a sensor out of the water, out of the mud, out of the environment that would harm it. You know, there are older ones that are analog. We just use the SDI-12s now because they're just so much easier. to work with, and they're lower power than the analogs. A nifty thing about the radars that a geomorphologist company like ours would appreciate is that it tracks channel invert between flow events. Now here, a flow event usually means the channel was dry, then a big flow comes through, and then it's dry again. And so from dry to dry, we often have channel elevation changes, and the radar will pick that up. It'll let us know what the elevation was before the flow and after. So if we're seeing any trends in aggradation or degradation, that's kind of a bonus bit of information that we get with these non-contact type sensors. So they are relatively more expensive than a pressure transducer, but they tend to be easier to install and maintain, so you save a little on your labor cost, depending on the layout of your site. They are made to be able to be mounted directly outdoors in the rain. I don't know that they do well if they got submerged accidentally, from a flood, but they wouldn't work good in that case anyway. They have a nifty thing called a blanking option. Say you've got a bridge that you're mounted to, but you've got maybe a shelf a little further down, like a top of a pier cap or something that's maybe impinging out into the radar beam a little bit and giving you some false returns. You can easily program a blanking section in the field. You just tell the sensor, especially these FTS SDI-12 ones, you just tell it how far from the sensor the impingement is, the angle or corner, and it'll just blank that out. And it works pretty cool, we found. They're sturdy too, but we do put them inside of housings, and I'll show you a couple examples later. Ultrasonics. We thankfully don't use these anymore. Probably 15 years ago, they were a decent option for non-contact. The radars weren't quite out yet. They are in their infancy. The ultrasonics are using sound waves to do the same job as a radar, to measure the time it takes to get down to the water and back, to measure your distance. Because they are in the sound spectrum of the radio range, you can actually hear them chirp like a bat. They're real susceptible to temperature changes, and they had a hard time, even with their internal temperature compensation, to give that good feedback the sensor needed to tell how hot the air was, so it could adjust its algorithms for calculating the distance. Some of that is just the sensor in Arizona would just get so hot, even in the shade, they just heat up. And so we didn't have great luck, and they died after 2 or 3 years anyway. So they just weren't robust. So I call them kind of fiddly, and I wouldn't recommend them for flood warning. And especially if you have a long distance to measure, like 30, 40, 50 feet. I think some agencies still use them in real precision measurements that are in a controlled environment, but not the greatest for us. Moving on to bubblers. Bubblers are great. They've been around a while. They're very accurate. The basic principle is, there's a gas or air source up in the housing where your gauge is, where your equipment is. There's compressed gas. One way or another, gas is compressed. It's forced out at a constant flow rate through a small tube, an orifice down into the water. The deeper the water, the more pressure it takes to force the air out at the same flow rate. So as the water goes up, more pressure is needed to force that air bubble out. So they call them bubblers. A pretty ingenious design. In the old days, they looked like this in the lower left. There was actually bottles of compressed gas on site. As you can imagine, they took a lot of room and a lot of maintenance and a lot of strong guys to lift these things into difficult areas. You could actually see in the regulator here, you could see a bubble going through that was showing you that is the regulated rate. Nowadays, they're more compact. They use less power. They can fit in smaller areas. They're still considered kind of bulky, but they have arrived, and they are useful now for flood warning. And they aren't just for the USGS doing high precision stuff. They're for us doing flood warning also. I say it's mostly a non-contact sensor. All the stuff that matters, the expensive stuff, is up here out of the way, and it's out of the flood zone, hopefully. The only thing that's in the water is that very inexpensive pipe of, or line, polyvinyl line of some kind. They have everywhere from analog to SDI12 options, and obviously SDI12 is always the best alternative. They are more expensive, so that's kept a lot of our clients out of the market for them, along with their bulk, and they need a lot more power typically. All that is improving though, so you should keep your eye on this and watch. Like Pima County's now got one on a flood warning site, and they're having great results over the last few years. I think Lynn said that they only had the line clog one time through kind of a fluke event, but basically these things keep the lines unclogged through a purging routine that you can time, have it do it every 5 minutes or something would be typical, where it supplies a higher rate of gas for a short burst through the line to just keep it cleared out. So they're well thought through, they're becoming very reliable, and the cost is coming down too. So they're down in our range for sure. And they are, they give you good, accurate results. Acoustic, so we haven't used bubblers yet. Acoustic Doppler profile, haven't used those either. They are one of those more expensive, more power hungry, bulkier options. I don't even have a nifty drawing for you. You guys are probably disappointed you didn't see my drawing, but the idea is that they profile the current or the actual velocity. They can give you a velocity profile from the bottom of the channel or pipe up through the top. Instead of, most stage gauges, we just get a depth and then we apply theoretical calculations to determine velocity and discharge. These actually measure the velocity at different levels throughout the profile, and they also keep track of the channel geometry. There are some that look up from the bottom of the channel, and there are some that emanate the energy from the side of the channel and can measure very large bodies of water, moving water, highly accurately, and even kind of keep track of where the bottom of the channel is, say if it's subject to erosion during high flows or anything. So there's ladder and bottom mount options. They can work underneath the ice just fine. They're really good for certain types of applications. For our typical flood warning stuff in dry, desert environments where the wash is, dry most of the time, we still probably wouldn't look at an option like this. I'd look at it for maybe a big river or something where there's water in it all the time. It's hard to measure. Some high sediment loads can cause some issues with this. You won't get enough return on the energy from the sensor. So, and too clear of water will also cause problems because there's not enough bubbles or, sediment in the water for that to get that return of the signal that the sensor needs to measure distance and velocity and everything, get that Doppler effect of measurement. So that's all I know about them. So now we've covered most of the types of sensors that are out there that are, in range of flood warning types like us. So we'll just talk a little bit now about some open channel hydraulic concepts. I'm not going to have any equations here, just some ideas and concepts that we should keep in mind while we're looking for a place to put a sensor. I'm assuming that you've already decided, hey, we need a sensor on this bridge or in this reach because this is really important to the community downstream. Or we've run a little bit of modeling, and this is where the model says would be the best place for us to put a sensor. That's where we start. I'm assuming you already have your place picked out. That would be a whole nother talk to talk about where to place the actual station. Now we're just talking about, now that you've picked your site, where do you put your sensor? How do you decide what type of sensor, all that kind of thing. Then we'll just talk through some examples instead of talk through everything we know about it. We'll just look at some photos. I like pictures, so pictures are fun. Here's an open channel hydraulic consideration. The name of this talk is Collecting Stage Data. Stage is different than the depth of the water, by the way, and I just wanted to make sure there's that clear distinction. In this little illustration here, another one of my great works, say this is a dam, or it could be a weir or any structure, and there's a ponded area in front of it. we're looking crossways to it. Say on the left is an emergency spillway, and we've got our pressure transducer down here at some elevation. We don't even know what it is, but we've surveyed and we know that it is 5 feet below the brink of the emergency spillway. Well, in this example here, this sensor is going to tell us, say it's a pressure transducer, it's going to tell us that the depth of water over the sensor is probably around 6 feet. It's about 6 feet in the water. 6 feet of water doesn't tell anybody anything really, because we don't really know where the PT is in relationship to the top of the dam and all that. But with a simple survey, we do know. We know that this sensor is 5 feet below the brink of the spillway, the emergency spillway. That brink of the emergency spillway is a really important thing in dam safety. That's what everybody's really concerned about, that and the top of the dam. Those are important elevations. So instead of reporting this as 6 feet deep, we would say this is about 1 foot deep in the emergency spillway. This is +1, roughly. That tells emergency managers way more than 6 feet, because that tells them, hey, at +1, then I do emergency action 1 that's in my emergency action plan for the dam. And if it goes +3, I know what to do. +3, I do another thing for my emergency response. So that's really helpful, clear information to give to someone like an emergency manager. If this were a weir in a fish hatchery, this would tell the hatchery fish manager, hey, I've got maybe 1 inch through this weir, and we've got 800 gallons per minute going through, and tomorrow we're going to give the fish a dose of some medicine that helps them stay healthy. And I need to know how much that medicine to put in at what flow rate, so I get the right concentration of this medicine. And it's a real thing. So they need to know what the flow rate is through not only the depth, but also the flow rate through the weir. So there's all sorts of ways to translate. But stage, there's stage for you. Stage is not depth necessarily. Hopefully that's clear. Hopefully that's helpful. I had somebody ask about stage one time, and I was kind of like, how do I explain this? Didn't have a great drawing. So another idea just to take away, I say this term all the time. It's, if you Googled it, it probably wouldn't show up. It's my term probably. I don't know. It's a hydraulic modeler's term is what it is. Control section. Anything that's a stable feature or channel reach that causes predictable hydraulic behavior is a control section. So the control section in this example, in this photo, is this weir. This is on a hatchery. The weir provides very precise control, it controls the amount of water that goes out so that you can measure it accurately, measure the actual flow rate accurately. In this case, we would put our instrument on the upstream. It's usually always the same case. You always want to be upstream of some control feature, whether it's a bridge, whether it's an unbridged crossing, a weir, emergency spillway, anything like that. In this case, we have a pressure transducer up in the pool area upstream of the weir, because weir equations rely on the size or the shape and size of the notch, and it wants to know what the depth is upstream of the weir. And you'll notice here, the water surface isn't flat right upstream of the weir. It's actually sloping down. You can tell that by the color change here. You don't want to put your pressure transducer right on the weir plate, for example. You want to have it usually 4 times the depth of the weir upstream of the weir. It's where we would have a transition to what's called critical flow if you're a hydraulic modeler. But it's a place where if you have that information, then you can plug it into your weir equation and you can predict what the discharge is very easily. So that's why people use weirs. That's why the pressure transducer is on the upstream side of the weir. If you had something measuring downstream here, you wouldn't have any reference to the weir because you're downstream of the weir. You would have to do some other hydraulic modeling based on the downstream conditions from the pressure transducer or whatever you're using. So hopefully that makes sense. General rule of thumb, in moderate to high grade, stream channel reaches, if you're running what's called subcritical, that means subcritical flow is tranquil flow. It's flow that's not raging. technically it's where your forces of momentum are roughly balanced or less than the forces of gravity. So there, that's as technical as we'll get. But you guys can all have a feel for that. You've been out in water. What's downstream kind of controls things more than what's upstream of the sensor. And hopefully I didn't just totally confuse everybody with that. We can always circle back on that later. So here's our control section right here. It's just a straight channel reach. It happens to be one of the straighter reaches along this part of the river. So we chose a place to put our sensor that was straight, that actually had some bank protection on one side, which helps keep it stable. You know, we want it to be a stable structure that won't change shape while the flow rises. You know, if the shape changes as the flow rises, we lose track of what the actual magnitude of flow is, for sure. And then we can't really warn downstream, hey, here's what's coming. We don't know because the channels change too much. And so we look for things like that, rock outcrops, bridges, road crossings, that kind of thing for our control section for flood warning. And we remind ourselves all the time that this is for flood warning. We're not trying to measure every drop. If we were, we'd be using weirs and things like that, which aren't really useful in large channels. And weir equations don't go up very large anyway. They're not meant for that. So speaking of bridges, bridges are great places to put gauges because they're accessible. Usually the channel's neck down at the bridge because they've had to grade the bridge approaches in tight to minimize the length of the bridge. So you've got water squeezing through a point where you can put a radar or a bubbler or a pressure transducer or whatever you have. But hydraulics through bridges can be tricky if you're trying to establish a rating curve. You know, if in flood warning, we're not trying to get a rating curve that's super accurate. We want to know, is it 100 CFS? Is it 500? Is it 10,000? Is it, you know, a million? We want to know a relative magnitude. So bridges are fine, but hydraulics are tricky through bridges anyway. So you're not going to get super high accurate measurements at bridge locations, but they're great places to mount sensors. So that last example showed low flow through a bridge. This is what high flow looks like. This is why I say bridge hydraulics get tricky. There's a lot of unknowns around bridges because the piers introduce a lot of turbulence and loss. Should the water come into contact with the top of the bridge, you have things like this happen with the water surface. You have an orifice situation and pressure, weird pressure flow in through this region here. Flow coming in toward the bridge is starting to slow down on the upstream side of the bridge. And when you slow water down, especially in the Southwest and any river laden with lots of sediment tends to drop out. Trees and stuff floating down the river are going to get caught up on the piers and make them even more, block even more of the flow. A lot of you have seen this. You've been out, you've watched bridges in high flow situations. It's interesting that the flow quickly, you have all these entrance losses to the bridge, but once the water gets down in this range in the middle of the bridge, it actually speeds up. Your velocities increase, you get scour around the piers, like sometimes very significant deep scour. Here in Arizona on the Salt River around Phoenix, it's a very large channel. We put piers down like 100 feet so that they don't wash out in the big events. And then you have increased velocity, but someplace down in here, the velocity decreases again. So again, when velocity decreases, all that stuff that was scoured out here, the material that was entrained, it's gonna dump out somewhere down here. So this is just to give you a little feel for the dynamics happening around a bridge. The best the most we know around a bridge hydraulically is this upstream area. We feel the models are pretty accurate up here. Like if you're doing a HEC-RAS or a Flow 2D, down in this range, there's a lot less known of the hydraulic characteristics. However, I will say this also, if you're doing flood warning, you know, where would you want a radar sensor? Here where it can get smacked by trees and submerged and destroyed, or maybe you want to put it down here on the downstream side. You don't have as good a rating, but the sensor will survive. And that's kind of what we want. We want the sensor to survive the floods so we can warn people. So this is just another thing to, a little drawing just to show what happens to the bed, how the bed deforms during these big flow events. So that's another thing that's going to impact your rating curve. I promise not to talk about rating curves too much, but a rating curve is a whole nother talk. Rating curves are great. They help you transmit information to downstream people better, like transmit actual magnitude and what it could do to them, as opposed to only knowing stage in a location. That's a whole nother talk we've done. We can do that another time. But debris and sediment considerations, we put this one in a long time ago, and it was always a clear area in the channel. And then all of a sudden it decided to be the place where trees like to accumulate, right underneath our radar box. So later we came in and we moved it to the center of the span over here. Probably we should have been further away from this pier in the beginning, and we were kind of dumb and put it too close. So we were trying to get the low flow channel, which was right up against the pier. We decided, let's play it safe, put it in the mid span. We're not on the very bottom of the channel, but we're close enough. This is flood warning, so let's not worry about it. So just goes to show, you learn a lot over time, and you got to pay attention. So another type of control section that I mentioned was just a unbridged road crossings. Real common, we run into them all the time. Terrible drawing probably, but here's our blacktop. We're looking down along the road. Here in the Southwest anyway, I suspect it's the same in most places. Upstream, leading up to any kind of an unbridged crossing, you're gonna tend to get sedimentation. So they usually have some kind of cutoff wall on both sides, especially the downside. I didn't show the cutoff wall to keep the roadway intact and from going away during a flow event. Hydraulics are better known upstream of the road than downstream. Coming up to the road, we usually see the flow flattening out a little bit, dumping sediment, and then as it goes across the road, the water surface will thin out and speed up because it's a smoother surface. Obviously, it just came from maybe a rough channel to a smooth surface. It thins out, it goes fast. When it gets across the road, that fast moving water that has less sediment is hungry for more sediment because it's got more energy. So what does it do? It always chews out the downstream side of the road. So let's not put our sensor on the downstream side of the road. When water is falling like this, you have a lot of turbulence. You could have little short sections of supercritical flow going where momentum forces are way over the gravity forces on the water. So we don't know what's going on down here, but we'll have a better idea of what the open channel hydraulics are like up here if you care about rating curves. Again, this is where you're going to have less energy also. So your PT is probably, or your orifice line for your bubbler is probably not going to get ripped out here. We typically put these, we try to avoid these, but if it's all you got, we'll put a PT or a bubbler line. We would recommend putting it, nailing it to the cutoff wall on the upstream side and let it be covered by a few inches of sediment. It's fine because that area gets a little scour anyway, and it'll have clear view of the water during the flow event. So we're going to keep moving here. So some of the goals of sensor placement are obviously limit damage to the sensor itself. This is a photo from 2004 after a big fire in Arizona. This wasn't a culvert across the road. This was a stilling well that the USGS had installed probably in the 40s or 50s, and it had been there a long time. And all of a sudden we had a fire and a debris flow that took it out. We can't prevent all damage. They had it in the best place they could have it. We actually put some equipment in it too after they abandoned it, used it for a couple of years until it blew out, and then we put something new in later. So you do what you can, but we do try to keep an eye on, potential damage to the site so that it keeps running during the flood and helping give us good information. The other thing that we need to really pay close attention to, set aside the rating curves and set aside, ooh, this is the ideal spot. We need a safe place to put that darn thing so we can get to it, to install it and maintain it. And we need to consider the rating curve after that. So I list rating curve factors after that. Mostly we need it to run right and we need it to give us good data. So sensor placement. Let's start with just natural environments. Most of the stuff we do is in natural environments. Most of our clients are the smaller rural communities that don't have any staff to do this. So we're out there in the hinterlands, installing and maintaining these things. We tend to avoid placing conduit in these overbank areas where there's lots of sediment moving, coming and going over time. Instead, we look for rock outcrops, obviously. A lot of this goes without saying. It's probably way rudimentary for some of you, but I figured we need to at least cover the rudimentary stuff too, and then we'll hopefully have some better tips in here later. So we look for rock outcrops. This is also a place that squeezes the water over. It's a pretty stable channel situation because of the outcrop, and the channel isn't going to move laterally on us because this is actually in a fairly, it doesn't look like it, but it's a pretty big deep canyon, and there's rock outcrops on the other side. So we've got a nice pinch point to put things. For pressure transducers and bubbler lines in high energy environments, we have learned the art of really armoring things well. We tend to use down in the low flow channel areas, 1.5 inch IMC, that's intermediate conduit or rigid, as some of you might know it. We use that a lot, and we nail it down really good because you can see from the size of the cobbles in this stream that this is a high energy environment. This isn't a nice sandy bed environment with low flows, low velocities under 10 feet per second. This is 20, 30 feet per second, moving big cobbles all the time. So we've learned in most of the areas we work out in the rough area, in the rough country, to really armor these things well. We use the galvanized tower clamps. You know, these are the same clamps you use to put antennas, and that we use to put antennas on towers and to mount standoffs and things. These are excellent for mounting conduit to rock and concrete and everything. Highly recommend it. Don't use the thin straps you get at Home Depot. Those just won't do, and they rust really bad too. And we use the 3/8 or 1/2 inch concrete anchors, and we use, you know, we've got a few hammer drills, so invest in a good hammer drill. It's worth it. We never use flex conduit. Yeah, it's easy and everything, but it's you'll kill yourself trying to maintain it in the future. It'll blow out on you. It's hard to push cable through flex, so we just don't use it. It's not strong enough for what we do. Here's just a couple more examples of typical installations. This is a cliff in the Gila River. We put conduit bodies all over the place for access. You know, the rule of thumb is if you can't pull a cable through 2 90s in a row. You know, if you've got a 90 sweep or bend, you're gonna have to put a conduit body in before you get to the next 90, or you're gonna really struggle over the years if you ever have to change out a pressure transducer. This is about a 150-foot run, way up about, you know, 50 foot up a cliff, and it's a difficult site. We spent days putting this all in, but now recently Tyler and I had to replace the PT, and it didn't take us more than an hour because we had conduit bodies all over the place to aid in that. So don't spare the conduit bodies, and use really big anchors and heavy stuff. And this stuff here has been in for years now, and there's no rust or anything on it. It does just fine. Just a little note, I was kind of pulling in a lot of random notes and things, but you know, tips and tricks from the years. If you're working on a structural steel bridge, you shouldn't drill into the structural steel. That's a no-no, because it isn't that it'll introduce a weak spot as much as rust. Rust is the bad guy with structural steel. So we never drill into them. You know, we're always permitted to be in these places anyway, and they would always rather not have us drill. So we use clamps. There's all sorts of clamps you can use for attaching conduit to the steel. And this one, this is a radar box, a radar housing. The radar is inside of this little box. We mounted it to a big plate, which was bolted to angle that we brought, and then we just used big all threads that went clear through. We made just basically a huge clamp that clamps through the bridge members rather than drilling in to the bridge. And this is also nice because we can move it easy too. We've already moved this one once when the channel shifted. This is on Aravaipa Creek in central Arizona. So never drill in the structural steel. Here's just another thing we like to do. in placing sensors. Here's a pressure transducer. You see it down here in the junction box. This is a standard alert standpipe up on a dam in Arizona. And the conduit is probably 150 feet in this case, and it goes way down into a lake. And it doesn't go real steep, so that you couldn't just let the weight of the pressure transducer feed itself down. It's not steep enough. So what we've devised and we've used for over 10 years now at our lake sites in Arizona is just a simple, put a bolt through the very end of the conduit at the deepest part of the lake with a copper bushing. The bushing is just copper pipe is all. And we loop this monofilament weed whacker line through that bushing, around that bushing, and it's taped to the PT on one side and it comes out the other. So if you can imagine, it's just a pulley for pulling that PT down to the bottom to make sure it gets locked hard against that bottom bolt there. And yeah, we don't have caps or anything in the bottom. We'd rather have sediment be able to move in and out easily and not get trapped in there. So a bolt through the end of the pipe, it's not glamorous, but it works really well, whether you're in an open channel environment or down at the bottom of a lake. And this monofilament just lasts forever. We have to retape it every couple years. It's simple and non-technical way to do something, and it's just cheap too. So a little tip. Wherever conduit is buried and against the soil, we always wrap it, or it'll rust pretty quick, even in Arizona. Here's just an example of grounding. This is another radar sensor housing, getting ready to put the radar in there, and we always ground everything because lightning's a big thing in Arizona, as it is everywhere. And we usually ground the conduit. Sometimes we'll run ground all along the conduit if it's not all connected well. This conduit doesn't have any expanders on it like for bridge expansion, so it's complete and we can get a good ground from there back to where the conduit hits the soil. And over on this side, we'd put a ground rod and ground it all too. So a couple little things. This is just to throw out quickly, this is a typical newer design that we really like. We've done a lot of these using the High Sierra traffic cabinet. It's a real simple 1 or 2 day type install design. This particular one's on a wing wall entry to a culvert. You can see it's got a pressure transducer conduit coming down. Very simple to install, very sturdy. In a kind of an urban-y environment where there's homes and stuff, this kind of structure looks at place, it looks at home. We do use round standpipes sometimes still on new installations, but usually out where we want a softer look, if it's out in the forest or something like that, where we don't want to attract attention with a traffic cabinet with all of its angles and shininess and everything. So just to show an example of how you can do string gauges real simple. Got another one here. Again, I mentioned the bolts on the bottom of the pipes. That works way better than we used to use a lot of these, just caps on the ends. But in Arizona, we just have so much sediment and flotsam in the water that it just packs up and it makes the PT not work so good. Another thing here on this right photo, flow is from right to left here. It's one of our large rivers in Arizona. We always try to angle the PT down and away or in the direction of flow, just so it doesn't catch so much debris, and debris will glance off of it rather than get packed and caught up in it. So just another little consideration for sensor placement. How you run the conduit is everything. This is next to a USGS site. They just went straight down and they catch a lot of stuff. There's always trash and junk stuck on theirs. Ours seems to deflect it pretty well. Plus we set it in, we jackhammered, chiseled out a channel for it so it stays kind of flush so it doesn't get the big stuff. This is kind of our Econo, we call it our Econo radar sensor station. It's a 1-day install. You bolt it onto the bridge, it's pretty cool. Here you see the whole site where the radar is looking out the bottom of the High Sierra traffic cabinet. And it's just looking straight down at the ground. It's nice that we don't have a river flowing, so we could actually climb up from below. It's just 2 pieces of angle bolted to the bridge and bolted to the box. It's real simple to level everything up with this kind of simple design. And then you can see here inside the cabinet, there's our battery, there's our radar sensor mounted to the bottom, looking out the bottom. We really like these. They're economical, quick to deploy. You can move it if the channel moves, you can move it if you want. But if this is all you have, you're looking at just a wide natural channel out in the middle of nowhere. What do you got? Well, our client really wanted a stream gauge here, and there was nothing for miles to, no rock outcrops, no nothing. We have a tree. So just this last year, we attached our first one to a tree ever. I wouldn't highly recommend attaching to trees, but it was all we had. Where we had to trench across a lot of overbank with a lot of loose alluvium that could be eroded during a big flow, because this is all in the floodplain here. This would all be inundated. We put the box up as high as we thought we should to avoid flooding. But the conduit's gonna be tricky. So we've done this in other places where we just drive unistrut to refusal. We put a trench in, drive unistrut to refusal, and then use those heavy clamps to attach our conduit with the PT in it to the unistrut. We've also used unistrut clamps too, and they work pretty well. The heavier clamps just makes us feel better. So unistrut's great. We've had several sites using it for years, and it stays put pretty well in high erosive environments. So one last couple slides on safety. Again, this is a site where flow comes from the right side of the frame to the left. We would have maybe liked to put it on the upstream side for better rating, but it's flood warning, we don't care. And we had safer access with the sidewalk on the downstream side. So we like to be able to stay safe while we're doing our work. So that's a big important factor. Don't overlook safety when you're putting these things in, because you want them to be there for years. You want to be able to maintain them for years, and you don't want people getting hurt. Speaking of safety, one more thing from yours truly, the safety officer here at J.E. Fuller. Always have a written safety plan. Have an on-site safety meeting and document it. You got to document your safety and the meetings you have. Everybody should have fall protection where there's a risk of falling more than 6 feet, and have your personal protective equipment on, hard hats, sunglasses, glasses, and gloves and all. Make sure that those things are on hand and that your people use them so that we can all return home safely and be ready for the next big flood. So that's my little plug about safety. I like to add that in there because we've had our share of accidents. So I'll open it up to question. Brad, do we have some questions?
We do have a couple.
Yeah.
So I'll start with the first questions from David Murdoch, and he's asking if you need a special setup for the radar sensor in order to read invert or channel bed, and how do you know you're getting valid data from the surface that's not water?
That's a great question. First off, there in your setup, you reference it to the channel bottom if you can. If you can measure down there, there's in the setup on site, you tell it, hey, 0, the bottom of the channel is this, and then it measures everything up. It'll give you stage, so it's smart enough to give you stage. If you're looking at the data and you're seeing a lot of weird bouncing happening in several feet, it's having a hard time finding the water. We had one recently, that last one that I showed in the safety photo. In that case, we set it up, it seemed to be working great. It started bouncing between 4 and 0 feet, 4 and 0, 4 and 0, 4 and 0 all the time, and it was driving us crazy. We went out, we didn't notice that there was a little sharp angle down the wall on the traffic wall on the bridge that seemed to be catching returns and even output. So we just connected back up to it, did the blanking, said, hey, there's something in 4 feet from here, and ignore that, please. And then it cleared it right up. So they've thought of that. The manufacturers are pretty clever, and they've made it super easy to make those adjustments. And really, you have to look at your data. Before we go out, we look at data, stare at data, go, okay, what's going on out here? What are we getting into before we go troubleshoot? And you're gonna kind of see if it's bouncing around weird on you and scattering. The other thing with dry channels, sometimes we'll just have vegetation come up in between the flows, because they're dry or real low flow most of the time. And so we know, oh, look, it's creeping up. Let's go out there and do some weed whacking or something. So those are just a couple things that come to the top of my mind. Really, you have to look at the data.
Okay, so our next question comes from your co-editor of the transmission newsletter, Lee.
Who does
He's
most of the work
asked,
now, by the way.
we'll start giving him credit eventually. He's asking for the modern bubbler. Do you still have to bring in compressed gas?
No, you do not require compressed gas. They use little tiny pumps, and they have little tiny air cylinders to store. So they have a little bit of storage, and they have the pumps. And if you're out there on one of those sites, you'll hear it run every once in a while. The pump will run for a few seconds, and then it's right back off to top off its air chamber.
Cool. And then the last question I've got here, it's from Edward Reyes. I think he's with Overland Park, Kansas. Asked, do you have any plans on how you installed the radar in the enclosure that you talked about just a minute ago?
Yes, we do. And actually, I mean, I don't want to plug manufacturers too much, but if you buy the FTS, it comes with a side mount that we can mount right inside of the traffic cabinet. So it's super easy. You drill a hole, you basically just make a big hole in the bottom and bolt the mount to the side and line it up. So it's just a matter of lining it all up. High Sierra, it makes a nice little radar box. I don't even think they advertise it. It's one we asked them to make custom a long time ago, and they'll make them for us. And they have a really nice mount built into it. So it'll basically just sandwich the sensor in there. Theirs are built specific for Indris Hauser, but we've put the FTS radars inside of the High Sierra box with just some little minor modifications, drilling a couple bolt holes out. So it isn't, I don't know if I really have a drawing, but it's simple enough. You can get the pieces and put it together yourself.
All right, well, I appreciate the presentation today, Brian. I think you did a fine job. Just a reminder to everyone, this meeting was recorded, and so we'll get the link out to the recording on our YouTube site as soon as we get that processed and put up there. And then all of those that attended will get an email from me here in the next week or so with a certificate good for one continuing education unit for your ASFPM certified floodplain manager certificate. So with that, thanks everyone for coming. Please look on our website and look out on Twitter and other social medias for our next webinar at the end of May. And I'll terminate this webinar. Thanks for coming, everyone.
Thank you, Brad.